A boy born to Samoan parents is 56 times more likely to play in the National Football League than any other boy in America. Across rugby, wrestling, and heavy contact sports, athletes of Samoan descent maintain a disproportionate presence at the highest levels of global competition. This chart reveals a staggering contradiction. While Samoans excel in elite athletics, the same population simultaneously experiences some of the highest global rates of obesity and type 2 diabetes. This creates a biological mystery. Why does a single demographic represent both the peak of physical human performance and extreme medical vulnerability? This paradox reflects an evolutionary story spanning thousands of years, written into genetic adaptations shaped by their seafaring ancestry. 3,500 years ago, the Lapita people began a migration across the Pacific Ocean, settling vast distances in double-hulled sailing canoes. These voyages required weeks of exposure on the open ocean, demanding intense manual labor while crews managed unpredictable and scarce food supplies. Survival under these pressures favored specific physiological traits: higher bone density to support large muscle attachment points, and a genetic baseline for lower myostatin levels, which allows for greater natural muscle development. The modern Samoan physique is the result of these traits being selected and refined by the extreme physical hardships of the ocean. Researchers at Brown University identified the specific mechanisms behind this physical profile in a 2016 genomic study of 5,000 Samoan individuals. This diagram highlights a variant of the CREBRF gene, found in roughly a quarter of the Samoan population. This specific genetic marker is almost entirely absent in European and African populations. This variant instructs cells to ruthlessly conserve energy. When the body takes in calories, the CREBRF gene prioritizes storing them as fat to ensure survival during long periods of famine. This mechanism aligned with the traditional Fa Samoa lifestyle, which centered on intense communal labor, including building, farming, and fishing. A diet of complex carbohydrates like taro and lean proteins like fresh fish provided the exact fuel required to support this physically demanding way of life. In this ancestral environment, the CREBRF gene functioned as a highly efficient biological engine designed to prevent starvation. Mid-20th century globalization abruptly displaced this traditional system, bringing rapid economic and dietary changes to the islands. Highly processed imports like canned meats, refined carbohydrates, and high-sugar products flooded the local market, replacing traditional food sources. This created an evolutionary mismatch, where a population's perfectly adapted traits suddenly collided with a radically different environment. Today, the CREBRF gene reacts to a caloric surplus by behaving as if it is still on an ancient ocean voyage. It blindly stores processed calories as fat because its cellular instructions have not changed. This sudden shift in the food environment turned a biological survival advantage into a significant health vulnerability. Recognizing the science of the CREBRF gene shifts the focus of the obesity crisis away from personal choices and toward the environmental impact of globalization. The modern Samoan physique remains a testament to ancestral resilience, a living record of physical history, currently navigating a modern world it was never designed to inhabit.